August 25, 2012. Pasadena, California, NASA Jet Propulsion Laboratory. The data coming back from Voyager 1 changes. For months, the spacecraft's instruments have been showing unusual readings. The level of energetic particles from the sun has been dropping. The level of cosmic rays from outside the solar system has been rising. The scientists monitoring the data know at this means. Voyager 1, launched in September 1977 and now traveling more than 18 billion kilometers from Earth, is crossing a boundary that no human-made object has ever crossed. On August 25, the transition is definitive. The solar particle count drops to near zero. The cosmic ray count spikes. Voyager 1 has crossed the Heliopause, the outer boundary of the heliosphere, the enormous bubble of charged particles and magnetic fields that the sun generates around itself and everything that orbits it. Voyager 1 is in interstellar space. The scientists celebrate. It is a genuine landmark. The first time anything made by humans has left the heliosphere after 35 years of uninterrupted travel. The measurements that follow over the next months and years are, literally, unprecedented. The first direct in situ measurements of the local interstellar medium ever taken. And those measurements do not match what the models predicted. The temperature in the compressed plasma region at the Heliopause is measured at somewhere between 30,000 and 50,000 Kelvin, roughly 10 times hotter than the heliosheath models had described. The magnetic field just outside the Heliopause is aligned parallel to the magnetic field just inside it, which the models had predicted should not be the case. And the Heliopause itself is not the smooth, gradual transition scientists had imagined, but an abrupt, turbulent boundary with sharp changes in particle density and magnetic field direction, occurring over distances far shorter than any model predicted. 6 years later, in November 2018, Voyager 2 crosses its own portion of the Heliopause, in a different location, on the other side of the solar system, in the direction of the southern ecliptic hemisphere. Its measurements confirm the Voyager 1 findings, and they add a new surprise. The Heliopause appears to be thinner on Voyager 2 side than on Voyager 1 side, suggesting that the heliosphere, the bubble that surrounds and protects the entire solar system, is not the symmetric shape that the standard models had assumed. Then, on September 24, 2025, NASA launched IMAP, the Interstellar Mapping and Acceleration Probe. It arrived at its observing position, the L1 Lagrange point, approximately 1.5 million kilometers from Earth, on January 10, 2026. On February 1, 2026, it began its 2-year primary science mission. Its job is to map the heliosphere from the inside, using a technique that the Voyager probes could never use. By detecting energetic neutral atoms that carry information from the distant boundary back toward Earth in straight lines, enabling the construction of a global map of the heliosphere's structure for the first time. The first results are still coming in. What IMAP finds about the structure, the physics, and the nature of the boundary that protects the solar system from the galactic environment will either confirm that the surprises from Voyager represent local anomalies, or reveal that the heliosphere is fundamentally different from what every model of it has assumed. And the scientists running the mission are paying very careful attention to every measurement it returns. The heliosphere is the most important thing protecting life on Earth that almost nobody knows exists. It is not the atmosphere, it is not Earth's magnetic field. It is something much larger. A bubble of solar wind and magnetic influence, extending far beyond the orbit of the most distant planets, that shields the entire solar system from the majority of galactic cosmic radiation that permeates interstellar space. Cosmic rays that would otherwise penetrate Earth's atmosphere and damage DNA, corrupt electronics, and raise cancer rates in surface life are deflected, scattered, and attenuated by the Heliosphere before they reach the inner solar system. The Voyager probes found that the Heliosphere's boundary is hotter, more turbulent, and magnetically configured in ways that the models did not predict. Now, IMAP is in position to produce the first comprehensive, high-resolution measurement of the Heliosphere's full structure. What that measurement will show is unknown. What it might show has scientists paying very careful attention. This video is about the edge of the solar system, the Heliosphere, the Heliopause, and the three specific discoveries from Voyager 1 and Voyager 2 that did not match any model's predictions. The wall of fire, the magnetic field alignment, the asymmetric bow undary. It is about why these three surprises matter for something more immediate than scientific curiosity. The effectiveness of the Heliosphere as a radiation shield for Earth, and the fundamental physics of how the Sun interacts with the galaxy. And it is about IMAP, launched September 24, 2025, now actively measuring from its position at L1, with instruments 30 times more capable than its predecessor IBEX, beginning the science that will either explain the Voyager surprises or reveal that the Heliosphere is more unusual than anyone modeled. By the end of this video, you will understand what the Heliosphere is and why it matters for life on Earth. What the three Voyager discoveries showed that no model predicted. Why the physics of the Heliopause boundary is a question that directly affects our understanding of how the Sun interacts with interstellar space. And what IMAP is doing right now that will produce the first comprehensive measurements of the Heliosphere's structure at the resolution needed to answer the questions Voyager raised: what is the Heliosphere? And how does a bubble of solar wind protect the entire solar system from the majority of galactic cosmic radiation? What did Voyager 1 find at the Heliopause that was 30,000 to 50,000 Kelvin, when models described a much cooler boundary? And why did the magnetic field alignment outside the Heliosphere match the inside when every model said it should differ? Why does it matter that Voyager 2 found the Heliopause thinner on its side than Voyager 1 found it on its side? And what does THIS suggest about the Heliosphere's structure? What is the IBEX ribbon? The band of enhanced neutral atom emission surrounding the Heliosphere that was discovered in 2009 and remains incompletely explained after 17 years of study. And what is IMAP's specific ally measuring from its position at L1? And why will its data provide information about the Heliosphere that the Voyager probes, despite being inside and then outside it, could never provide? This is not a video claiming that the Heliosphere is about to fail or that life on Earth is at risk from cosmic rays. The Heliosphere has been protecting the solar system for 4-6 billion years. It is not weakening in any sudden or alarming way. This is also not a video treating the Voyager discoveries as merely interesting details in a system we otherwise understand. The three specific surprises that Voyager 1 and 2 found at the Heliopause, each of which was inconsistent with the models built over decades, represent specific gaps in the understanding of the most important radiation shield in the solar system, and they call into question specific physical processes that the models were built on. IMAP primary science mission began February 1, 2026. This is not a past discovery. It is an ongoing investigation, and its results will be among the most important findings in heliospheric science in decades. The honest version of this story is that we are at a specific and datable moment of maximum uncertainty about the Heliosphere's boundary physics, between the Voyager surprises and the IMAP results, and that moment is right now. Before we go further, if the kind of story where the most important protection system for life on Earth turns out to be less understood than the models described, and where a brand new mission is actively producing the data that will change that understanding, is what you come to Galaxy Pulse for. Subscribe. Now, back to the edge of the solar system, and to the wall of fire that nobody expected. The Heliosphere, the Heliopause, and what Voyager found base explanation. The Sun continuously emits a stream of charged particles, electrons and protons, moving outward from the solar corona at speeds of 400 to 800 kilometers per second. This stream, called the solar wind, extends in all directions from the Sun, filling the solar system with a thin, magnetized plasma that carries with it the Sun's own magnetic field, stretched and wound into a spiral pattern by the Sun's rotation. The spiral pattern, called the Parker spiral, after physicist Eugene Parker, who first described it mathematically in 1958, means that by the time the solar wind reaches the outer solar system, the magnetic field it carries is wrapped almost perpendicular to the direction of solar wind flow. The solar wind does not travel forever. At some distance from the Sun, it encounters the interstellar medium. The diffuse gas, dust, and magnetic fields that fill the space between stars in the Milky Way. The pressure from the solar wind and the pressure F-rom, the interstellar medium, reach an equilibrium, and the boundary between them is the heliopause. Inside the heliopause, the solar wind dominates. The magnetic field is the Sun's magnetic field, extended outward by the wind. The particle environment is shaped by the Sun's activity. More energetic during solar maximum, calmer during solar minimum. Outside the heliopause is interstellar space. A completely different environment, dominated by the magnetic field and plasma of the Milky Way's interstellar medium, enriched by material ejected from supernova and stellar winds across billions of years. The region between the outer planets and the heliopause is called the heliosheath. It is where the solar wind has slowed from its supersonic inner solar system speed to a subsonic flow, having passed through a shock called the termination shock, where the wind abruptly decelerates as it approaches the boundary of the interstellar medium. Voyager 1 crossed the termination shock in 2004, at a distance of about 94 from the Sun, and spent 8 years traveling through the heliosheath before crossing the heliopause in 2012. Voyager 2 crossed the termination shock in 2007 at about 84, closer to the Sun on its side, suggesting that even the inner heliosphere boundary is asymmetric. The termination shock is where the solar wind first encounters the resistance of the interstellar medium and slows from supersonic to subsonic velocities. Beyond it, in the heliosheath, the solar wind is moving more slowly but is still moving outward, carrying its magnetic field, until it reaches the heliopause. The heliosheath is a turbulent, compressed zone where the solar wind plasma is piling up against the interstellar medium's pressure. A region that both Voyager probes spent years traveling through before reaching the boundary itself. The heliopause is located at approximately 120 from the Sun in the direction Voyager 1 traveled, roughly 3 times the distance to Pluto, at about 18 billion kilometers. Because the heliosphere is moving through the interstellar medium as the Sun orbits the galaxy, it is not symmetric. The direction toward which the Sun is moving through the interstellar medium, called the nose of the heliosphere, has a more compressed, abrupt boundary. The trailing direction, the tail, extends behind the solar modion. The heliosphere was generally expected to resemble a comet, a blunt, compressed leading edge, and an elongated trailing structure. This is the model. The reality has been considerably more interesting. Normal versus strange contrast under the standard expectation. Crossing the heliopause should involve a transition from the solar wind of the heliosheath to the cooler interstellar medium, with the magnetic field rotating from the roughly azimuthal direction it carries in the heliosheath H to the direction of the local interstellar magnetic field, which models suggested should be oriented differently. Voyager 1 found something else. The temperature of the plasma in the compressed region at the heliopause was measured at approximately 30 to 50 Kelvin. This is far above what had been modeled for the region near the heliopause, where the solar wind has been slowing and cooling, CNCE crossing the termination shock. The region became known in media coverage as the Wall of Fire. Not because the plasma poses any danger to the spacecraft. The particle density is so low that very little energy is transferred despite the high temperature, but because the temperature reading vastly exceeded what the models had described. The most likely explanation involves the compression and magnetic trapping of energetic particles at the boundary. As the solar wind piles up against the incoming interstellar medium, particles are trapped and compressed, heating to far higher temperatures than simple models predicted. The magnetic field produced a second surprise. Models of the interaction between the heliosphere and the interstellar medium predicted that the magnetic field just outside the heliopause would differ in direction from the field inside. This difference was expected to be one of the clearer signatures of crossing from solar-dominated to interstellar space. Instead, Voyager 1 found that the magnetic field just outside the heliopause was running parallel to the field just inside it, not similar, parallel. The fields matched in direction to a degree that was unexpected. When Voyager 2 reached its portion of the heliopause in November 2018, NASA reported. An observation by Voyager 2 magnetic field instrument confirms a surprising result from Voyager 1. The magnetic field in the region just beyond the heliopause is parallel to the magnetic field within the heliosphere. Two measurements, on opposite sides of the solar system, confirming the same unexpected magnetic alignment. And Voyager 2 added a third surprise. The heliopause on its side appeared thinner than on Voyager 1's side. The transition was more abrupt, occurring over a shorter distance. This asymmetry between the two sides of the heliosphere suggests that the heliosphere's structure is not uniform. The boundary has different properties at different locations around its surface. Full detective breakdown. The three Voyager surprises, the unexpected temperature, the unexpected magnetic alignment, and the asymmetric boundary, are not minor corrections to a model that was otherwise correct. Each one challenges a specific and important assumption about how the heliosphere interacts with the interstellar medium. The temperature finding challenges the understanding of how energy is dissipated at the heliopause. The standard picture has the heliosheath filled with solar wind that has progressively cooled since being shocked at the termination shock, arriving at the heliopause at temperatures in the range of a few thousand to low tens of thousands of Kelvin. Instead, a hot, compressed plasma layer is found at the boundary. The physical mechanism, likely involving the compression and trapping of energetic particles air. The magnetic fields of the heliosphere and interstellar medium press against each other, has not been fully quantitatively confirmed. The detailed mechanism of energy deposition at the heliopause remains an active research problem. The magnetic alignment, finding challenges, models of the interstellar magnetic field near the heliosphere. If the interstellar magnetic field just outside the heliopause is running parallel to the heliospheric magnetic field inside, the interstellar medium S field in the solar neighborhood may be aligned with the heliosphere's field by coincidence. Or, the heliosphere itself may be reshaping the interstellar magnetic field in its immediate vicinity through some physical interaction. As NASA noted after the Voyager 2 confirmation, the parallel alignment challenges earlier assumptions about how the Sun interacts with the surrounding interstellar environment. The asymmetric boundary adds a third layer. The heliosphere, as observed by the two Voyager probes at different locations, is not uniform at its surface. This is potentially significant for the heliosphere's shielding effectiveness. A thinner boundary in O-Ni direction may provide less attenuation of the galactic cosmic rays the heliosphere is supposed to deflect. If different parts of the heliosphere's surface are thinner or thicker by significant amounts, the shielding provided to the inner solar system va rise with direction in ways that the standard models did not capture. Beyond these three main surprises, the Voyager data revealed a fourth significant finding. The heliopause is permeable. Cosmic rays flow inward through the heliopause, even on the solar wind-dominated side, and solar wind particles leak outward beyond the heliopause. The boundary is not a hard wall, but a dynamic, partially transparent frontier where material flows in both directions. A detail that matters for calculating how much cosmic ray exposure the inner solar system actually receives. The question that all four of these findings raise is whether they represent the local properties of the two specific points where the Voyager probes crossed the heliopause, or whether they represent general properties of the heliopause across its entire surface. Two data points at two specific locations on a surface that spans hundreds of O in every direction are not sufficient to answer this question. IMAP is the instrument that will begin to answer it. Three concepts to make concrete. Three concepts need to be clear. The first is what galactic cosmic rays are and why the heliosphere matters for blocking them. Galactic cosmic rays are high-energy particles, primarily protons and atomic nuclei, accelerated to near the speed of light by sources throughout the Milky Way, including supernova remnants and pulsar wind nebulae. These particles permeate the interstellar medium. When they enter the heliosphere, they are deflected and attenuated by the solar wind's magnetic field, which scatters them and reduces their flux. By time galactic cosmic rays reach Earth, the heliosphere has reduced their intensity significantly compared to the interstellar medium outside. Without the heliosphere, the cosmic ray flux reaching Earth's atmosphere and surface would be substantially higher, with implications for the ionization of the atmosphere, the production of secondary radiation at the surface, and over geological timescales, potentially for the chemistry of the biosphere. The heliosphere is not the only protection. Earth's own magnetosphere and atmosphere provide additional shielding, but the heliosphere is the first and largest line of defense. The second is how IMAP measures the heliosphere from L1, rather than by traveling to the edge. Energetic, neutral atoms, ENA, are produced when fast-moving charged particles from the solar wind collide with neutral atoms drifting in from the interstellar medium. In these charge exchange reactions, the charged solar wind particle captures an electron from the neutral atom and becomes neutral itself, while the formerly neutral atom becomes charged. The newly neutral particle is no longer deflected by magnetic fields, and therefore travels in a straight line from wherever the collision occurred. Some of these ENAs travel inward, toward the Sun, and can be detected by instruments near Earth. By measuring the energy and direction of arriving ENAs, IMAP can map, its stationary position at L1, the conditions across the entire heliosphere boundary simultaneously, in a way that no spacecraft traveling to the edge can replicate. Because a Voyager-type probe is only at one location at one time, while ENAs arrive continuously from all directions at once, The third is what the ibex ribbon is and why it remains puzzling. The Interstellar Boundary Explorer, IBEX, launched in October 2008, provided the first ENA-based maps of the heliosphere. Those maps showed an unexpected feature. A band of enhanced ENA EMEs, Sion, running roughly in a circle around the heliosphere, called the ibex ribbon. The ribbon is brighter than the surrounding heliosphere in ENAs, suggesting a specific physical process producing excess ENAs along a particular arc of the sky. The leading hypothesis involves the interaction of the heliospheric magnetic field with the local interstellar magnetic field, where the interstellar field runs tangent to the heliopause. Secondary ENAs produced in the interstellar medium outside the heliosphere are FOC used toward Earth and produce the excess signal. This explanation is plausible and has some quantitative support, but it is not confirmed. After 17 years of IBEX observations, the ribbon remains incompletely explained. A map, with instruments providing RAUG HLY 30 times better sensitivity and resolution than IBEX, will map the ribbon at a level of detail that may finally resolve what causes it. Here is why the heliosphere's structure matters for something more immediate than scientific curiosity. The heliosphere shields the solar system from galactic cosmic rays, and the effectiveness of that shielding varies with the structure of the heliosphere's boundary. A thicker, more uniform boundary provides more consistent attenuation than a thinner or SI-metric one. If the heliopause is thinner in certain directions, as the Voyager comparison suggests, the cosmic ray flux reaching the inner solar system may be higher from those directions. For most purposes, this variation is not immediately alarming. The heliosphere has been providing its shielding for 4.6 billion years, and life on Earth has persisted through whatever variations in the heliosphere's structure have occurred during that period. But for specific applications, particularly for planning deep space human missions beyond the protection of Earth's magnetosphere, the specific structure and shielding effectiveness of the heliosphere matters quantitatively. Astronauts traveling beyond Earth's magnetosphere are exposed to galactic cosmic rays. The rate of exposure depends on where in the solar system they are and what direction they are traveling, relative to the heliosphere's structure. Getting those numbers right requires knowing what the heliosphere's boundary actually looks like. IMAP data will provide better inputs for these calculations than have ever been available. There is also a longer-term consideration. On geological timescales, as the Sun moves through different regions of the interstellar medium, the heliosphere has likely contracted significantly during periods when the Sun traveled through dense interstellar clouds. During any such period, the galactic cosmic ray flux at Earth would have been higher. How much higher, and whether this is relevant to geological or evolutionary events on Earth, is a question that requires knowing the heliosphere's properties well enough to model how they change. A map, right now, is producing the most complete dataset on those properties that has ever existed. The 3 Voyager surprises and the unexplained ibex ribbon describe a heliosphere that is more complex and less understood at its boundary than the models built without direct data had assumed. A map, from its position at L1, is right now collecting ENA data from the entire heliosphere simultaneously, building measurements with far greater sensitivity and resolution than IBEX. The principal investigator of IMAP, David McComas of Princeton University, has been direct about what he thinks IMAP will accomplish. Speaking in January 2026, McComas noted that what IMAP will primarily resolve is not whether the heliosphere has a comet tail or a quas shape, a debate that has received significant media attention, but rather the actual physics of the boundary interaction. how particles are heated, accelerated, and transported at the Heliopause, how the interstellar magnetic field INT interacts with the heliospheric field, and what the ibex ribbon actually is. Those are the questions EMAP is answering right now, and the answers will represent the most significant advance in understanding the boundary of the solar system since Voyager 1 crossed it in 2012. EMAP, the physics questions, and the deeper significance. EMAP launched on September 24, 2025, at 7:30 a.m. EDT, aboard a SpaceX Falcon 9 rocket from Launch Complex 39A at Kennedy Space Center, the same pad from which Saturn V rockets launched Apollo missions to the Moon and from which Space Shuttle missions departed for decades. Its destination was not the outer solar system. It traveled to L1, the Lagrange point between Earth and the Sun, approximately 1.5 million kilometers from Earth, where the gravitational influences of Earth and Sun balance, providing a stable observing platform. The mission was built by the Johns Hopkins Applied Physics Laboratory and is led by principal investigator David McComas of Princeton University, with an international team of 27 partner institutions. EMAP total mission cost is approximately $7.8 million. The mission carries 10 scientific instruments. 3 of them are specifically designed for studying the heliosphere's boundaries by detecting energetic neutral atoms. EMAP Low, EMAP High, and EMAP Ultra, covering different energy ranges and providing complementary measurements of the ENA flux from different portions of the heliosphere simultaneously. Together, these 3 instruments cover an energy range from about 0.1 keV to over 300 keV, spanning the range of solar wind particle energies relevant to heliospheric boundary physics. EMAP Ultra, built by the Johns Hopkins Applied Physics Laboratory, is the most capable ENA imager ever flown, providing imaging at energies where IBEX had limited sensitivity and at angular resolutions that will resolve structure IN, the heliosphere boundary, that IBEX could not detect. The remaining 7 instruments include charged particle detectors that measure the solar wind and energetic particles in the inner heliosphere, a magnetometer that measures the magnetic field at L1, a dust detector that measures interstellar dust grains entering the solar system, and the GLOWS instrument that measures the global solar wind structure through ultraviolet emission from hydrogen atoms. Together, the 10 instruments provide a comprehensive picture of the heliosphere's inputs, the solar wind and interstellar environment at L1, and its boundary conditions, the ENA emission from the heliosheath and heliopause. The spacecraft spins about 4 times per minute as it orbits L1, allowing its detectors to scan the entire sky in each spin. Over the course of a 6-month survey cycle, EMAP instruments build up a map of the entire heliosphere in ENAs at each energy range covered by the instruments, with roughly 30 times the capability of IBEX. The ENA detection method works as follows. In the heliosheath, where the solar wind has slowed and is mixing with material from the interstellar medium, charged solar wind protons collide with neutral hydrogen atoms that drift in from interstellar space. In these charge exchange reactions, the proton captures an electron and becomes a neutral hydrogen atom, retaining most of the proton's velocity. This newly neutral hydrogen atom then travels in a straight line, undeflected by magnetic fields, in whatever direction it happened to be moving at the moment of the charge exchange. Some fraction of these ENAs happen to be moving in directions that point back toward Earth, and EMAP detects them. From the energy and arrival direction of each detected ENA, scientists can infer where in the heliosheath the charge exchange occurred, how fast the solar wind was moving at that location, and how the solar wind's energy varies across the heliosphere's SDR aperture. Over months of observation, these measurements build into a global picture of the heliosheath and the heliosphere boundary. Why is this so much more powerful than sending a spacecraft to the boundary? A spacecraft at one location measures conditions at one point at one time. As it travels through the heliosphere, it can build up a trajectory's worth of measurements, which is Voyager did over 35 years of travel. But it cannot simultaneously sample conditions across the full sky in every direction. VNAs can, because they travel in straight lines from wherever in the heliosheath they were produced. They carry directional information about conditions across the entire heliosphere simultaneously. A map, sitting at L1, is continuously receiving ENAs from the heliosheath in every direction, from the nose of the heliosphere ahead of the sun's motion, from the flanks, from the tail region behind, and from the polar directions above and below the ecliptic. Each ENA carries a message about conditions at a specific location in the heliosheath. Reading all of them simultaneously is what produces the global map. The science phase began February 1, 2026. First results are still being processed. The first full ENA maps of the heliosphere are expected to be released in the first year of the science mission, with initial findings likely appearing in late 2026. The debate about the heliosphere's shape has received significant public attention. The two leading models are the comet tail model, in which the heliosphere has a long trailing structure extending thousands of O behind the sun's direction of motion, and the quas model, proposed by Merav Ofer at Boston University and collaborators, in which the solar magnetic field concentrated near the poles creates two distinct lobes that trail behind the sun rather than a single elongated tail. The shape matters in principle. Different shapes imply different distributions of the heliopause across the sky, and therefore different cosmic ray shielding properties in different directions. The comet model distributes the tail boundary smoothly behind the solar motion. The quas model concentrates the outer boundary in two specific directions. However, IMAP principal investigator McComas has noted that the shape question, while interesting, is not the most consequential question IMAP will address. The deeper questions are the ones Voyager raised directly. What physical processes produce the 30,000 to 50,000 Kelvin temperature at the heliopause? Why do the magnetic fields inside and outside the boundary align when they should not? What is the actual physics of how the solar wind interacts with the interstellar medium at the boundary? And what produces the ibex ribbon? IMAP global ENA maps will provide data relevant to all of these questions simultaneously. The shape will emerge from the maps, but the more important product will be the first spatially resolved measurements of how the heliosphere's boundary conditions vary across its entire visible surface, at the resolution needed to distinguish between competing physical models of the boundary's behavior. The heliosphere's boundary is not just a geometric shape. It is a physical system where two plasmas, the solar wind and the interstellar medium, separated by their respective magnetic fields, interact in ways that produce the temperature anomalies, magnetic C alignments, and ribbon structures that Voyager and IBEX revealed. IMAP will characterize that system at a level of detail that no previous instrument approached. The ibex ribbon is perhaps the most puzzling specific feature of the heliosphere revealed by modern instrumentation. IBEX, launched in October 2008, found a brighter than background band of ENA emission running roughly in a circle around the heliosphere. The ribbon is not associated with any obvious feature of the heliosphere's geometry in the standard models. It does no trace the heliosphere's equator, the Sun's poles, or the direction of the Sun's motion through the interstellar medium. The current, leading explanation involves the geometry of the local interstellar magnetic field, where the interstellar magnetic field runs tangent to the heliopause, secondary ENAs, produced by charge exchange processes in the interstellar medium outside the heliosphere, are produced more efficiently and travel in directions that happen to point back toward Earth. The result is a geometrically defined band on the sky, corresponding to the locus of locations where the local interstellar magnetic field is tangent to the heliopause. This explanation is plausible and has some quantitative support, but it makes specific predictions about the relationship between the ribbon's geometry and the direction of the local interstellar magnetic field, and these predictions are only partially consistent with other measurements of the interstellar field direction. After 17 years of IBEX observations, the ribbon remains the most prominent unexplained feature of the heliosphere's ENA map. IMMAP is one of IMMAP primary science targets. If IMMAP improved instruments reveal internal structure in the ribbon, or resolve W-Heather, the ribbon's geometry precisely matches the interstellar field direction prediction. It will either confirm or challenge the leading explanation, and, in either case, will constrain the interstellar magnetic field direction near the solar system with much greater precision than any previous measurement. The local interstellar magnetic field direction is itself a cosmically significant quantity. It reflects the large-scale magnetic structure of the Milky Way in the solar neighborhood, carries information about the history of stellar activity in the region, and determines how effectively the heliosphere is compressed in the direction of the field. There are three interpretive frames for what the Voyager surprises, the IBEX ribbon, and the IMMAP mission together represent. The first is the discovery phase frame. For most of the history of space science, the heliosphere was studied only from the inside, using instruments in the inner solar system that measured the solar wind and its magnetic field without ever reaching the boundary. The Voyager probes provided two data points at the boundary itself. IBEX provided the first global ENA maps, but at limited capability. IMMAP is the first instrument capable of producing genuinely comprehensive, high-resolution measurements of the Heliosphere's global boundary structure. We are, right now, in the first period of modern, data-rich heliospheric science, and the surprises encountered so far may simply reflect the inevitable gap between models built on limited indirect data and the really revealed by direct measurement. The second is the model revision frame. The heliosphere is significantly more complex at its boundary than the simplified models of a smooth, symmetric bubble suggested. The temperature is higher. The magnetic field behaves differently, the boundary is asymmetric and permeable, and there is an unexplained bright ribbon in the ENA sky. Each of these specific surprises requires a specific physical explanation, and the models that failed to predict them need specific revisions. The revisions may involve improvements to specific physical processes already included in the models, or they may require mechanisms not previously considered. The third frame is the most far-reaching. The heliosphere as a protective system whose properties directly affect the long-term habitability of the inner solar system. The galactic cosmic ray flux reaching Earth's atmosphere has varied throughout geological history, as the Sun has moved through different interstellar environments, and as the heliosphere has expanded and contracted. Periods when the heliosphere was smaller, during dense interstellar cloud passages, may correspond to periods of higher cosmic ray flux at Earth. Understanding the heliosphere's current structure precisely enough to model these historical variations, requires exactly the kind of comprehensive global characterization that IMAP is now conducting. What IMAP finds will be the most precise answer yet to the question: what is the heliosphere, and how well does it protect us? A note on why the heliosphere's cosmic ray shielding matters concretely. The abstract concept of cosmic ray shielding becomes concrete when you understand what galactic cosmic rays actually are and what they do to living matter. Galactic cosmic rays are primarily protons and heavier atomic nuclei, stripped of their electrons, accelerated to relativistic speeds by supernova, pulsar wind nebulae, and other energetic astrophysical processes scattered throughout the Milky Way. They arrive at the heliosphere from all directions, having traveled billions of light-years in some cases, carrying kinetic energies ranging from tens of millions to trillions of electron volts per nucleon. At the highest energies, individual cosmic ray particles carry more kinetic energy than a baseball pitched by a major league pitcher, packed into a single subatomic particle. When these particles strike biological tissue, they damage DNA. A single cosmic ray proton, traveling at nearly the speed of light, can create a track of ionization damage along its path through a cell, breaking chemical bonds and potentially causing mutatio NS. On Earth's surface, we are protected from most of this by three layers of shielding: the heliosphere, which reduces the flux of galactic cosmic rays compared to the interstellar medium; Earth's magnetosphere, which deflects the lower energy cosmic rays; and Earth's atmosphere, which provides absorbing material that creates secondary particle showers that are largely absorbed before reaching the ground. Beyond Earth's magnetosphere, astronauts lose the protection of the magnetosphere and atmosphere, retaining only the heliosphere's shielding. The galactic cosmic ray dose rates experienced by astronauts in deep space are roughly 100 to 200 times higher than those on Earth's surface. For a mission to Mars lasting 2 to 3 years, the accumulated cosmic ray dose is estimated to exceed the career dose limits set by NASA for astronauts in low Earth orbit. This is one of the primary radiation health concerns for manned deep space exploration. The heliosphere's shielding efficiency at different cosmic ray energies and from different directions in the sky is therefore not just an academic question. It is a practical quantity that affects how we calculate radiation exposure for astronauts on interplanetary missions. If the heliosphere provides less shielding in some directions, because the boundary is thinner or more permeable in those directions, as the Voyager asymmetry finding hints, then the radiation dose rates for missions traveling in those directions would be higher than current calculations assume. Mapping of the heliosheath structure across the full sky will provide the most accurate available data for calculating these direction-dependent shielding efficiencies. It is heliospheric science with direct engineering relevance to the human exploration program. Let's come back to where we started. August 25, 2012. Voyager 1 crosses the Heliopause. The data does not match the models. The plasma at the boundary is somewhere between 30,000 and 50,000 Kelvin, roughly 10 times hotter than the heliosheath models described. The magnetic field is aligned in a direction the models said it should not be. 6 years later, Voyager 2 crosses a different portion of the Heliopause and confirms both surprises while adding a third. The boundary is thinner on its side than on Voyager 1's side. 2 probes, 2 crossing points, 4 major surprises: a heliosphere that is hotter, more magnetically unusual, more asymmetric, and more permeable than every model built without direct data had described. Then, on February 1, 2026, IMAP began its 2-year primary science mission. The Interstellar Mapping and Acceleration Probe, stationed at L1, built by the Johns Hopkins Applied Physics Laboratory, led by David McComas of Princeton University, is right, No. W building, the first comprehensive global measurements of the heliosphere's boundary structure at the resolution needed to answer the specific questions Voyager raised. The physics of the wall of fire, the mechanism behind the magnetic alignment, the explanation for the ibex ribbon, the spatial extent of the asymmetry. Map data will address all of them. The results are still coming in. Coverage of the Voyager discoveries at the Heliopause has been significant and enthusiastic. The wall of fire framing, which appeared repeatedly in popular media in 2025, captured the temperature finding in dramatic terms. The magnetic alignment finding has been reported accurately, but several specific and important aspects of this story have been consistently missed or underemphasized. The first is what the temperature of 30 to 50 Kelvin actually means physically, and why it doesn't mean what it sounds like. In the plasma at the Heliopause, temperature is a measure of particle speed, not of heat as we experience it. The plasma is extraordinarily hot in the physicist's sense, particles moving very fast, but extraordinarily sparse. The particle density is so low that very little energy would actually be transferred to any object passing through it. The Voyager spacecraft themselves passed through the wall of fire without damage. The significance of the temperature is not that it's dangerous, but that it's far above what models predicted, which means something about the energy balance at the Heliopause, specifically how energy is trapped and accumulated at the boundary between the two plasma regions, was not correctly captured. The second is what the magnetic alignment finding actually implies for our understanding of the interstellar medium near the solar system. The parallel alignment of magnetic fields, inside and outside the Heliopause challenges, not just the model of the heliosphere itself, but the model of the interstellar magnetic field in the solar neighborhood. If the interstellar field near the heliosphere is running parallel to the heliospheric field, either by coincidence, by the heliosphere reshaping the interstellar phi-eld in its vicinity, or by some physical coupling mechanism, then what we know about the direction and structure of the local interstellar magnetic field needs to be revised. The implications extend from heliospheric science into the broader question of how the Sun and its environment interact. The third is the permeability finding, which received almost no popular coverage. The Heliopause is not a hard boundary. Solar wind particles leak out, galactic cosmic rays leak in. The net flux in each direction is determined by the pressure balance, but the boundary passes material in both directions. This means the heliosphere provides attenuating shielding from cosmic rays, not blocking shielding, and the degree of attenuation varies with the specific structure of the boundary. Understanding permeability quantitatively is essential for calculating how much cosmic ray exposure the inner solar system receives, but it is rarely discussed outside specialist literature. The fourth is the ibex ribbon and its 17-year status as an incompletely explained feature. An unexplained bright band surrounding the entire heliosphere, discovered in 2009, still without a fully confirmed explanation, visible in every ENA map of the heliosphere ever produced, essentially absent from popular coverage of the heliosphere's mysteries. The ribbon is the most prominent unexplained feature of the heliosphere's observable structure, and understanding why it exists is one of IMAP primary science objectives. The ribbon's explanation, when found, will reveal something specific about the local interstellar magnetic field, which is itself a window into the structure of the Milky Way in the solar neighborhood. The fifth is a nuance about the framing of IMAP science objectives. Popular coverage has often presented EMAP as primarily a mission to resolve the debate about the heliosphere's shape. Comet tail versus quas. But EMAP's own principal investigator, David McComas, has stated directly that he does not think the shape is the most important question. What EMAP will primarily advance is the understanding of the actual physics at the boundary. How particles are energized, why the temperature is so high, how the magnetic fields interact, and what produces the ribbon. The shape will emerge from the data, but it is a product, not the primary goal. The most significant current development is EMAP Active Science Phase, which began February 1, 2026. All 10 instruments are operational and recording data. The first, ENA measurements from L1, began arriving immediately upon the science phase start. The mission's timeline includes ENA maps of the heliosphere over the first 6-month survey cycle, which will be completed by approximately August 2026, and will constitute the first comprehensive ENA map of the heliosphere at EMAP resolution. The specific questions that the first maps will address include the spatial structure of the hot plasma region detected by Voyager, the detailed morphology of the ibex ribbon at EMAP, improved resolution, and the directional distribution of how heliospheric conditions vary across the full sky. The Voyager probes continue to provide in situ data from interstellar space. Both spacecraft are still operational, though with degrading power and instrumentation. Voyager 1, as of mid-2026, is more than 24 billion kilometers from Earth, transmitting data that takes more than 22 hours to reach ground stations. Voyager 2 is at a slightly shorter distance on the other side of the solar system. Both continue to measure the properties of the interstellar medium in their respective locations, providing time series data on how the interstellar environment varies as the Sun's activity changes. The Voyager data, combined with the IBEX historical archive and the EMAP measurements beginning in 2026, will constitute the most comprehensive dataset on heliosphere-interstellar medium interaction ever assembled. The science papers that will emerge from the first year of EMAP data, expected to begin appearing in late 2026 and 2027, will represent the most significant advances in heliospheric science in decades. 1. Additional context point. The New Horizons spacecraft, which famously produced the first close-up images of Pluto in 2015, is traveling outward through the outer solar system and is expected to cross the termination shock, the inner boundary of the heliosheath, in the 2020s or 2030s. Though New Horizons was not designed as a heliospheric science mission, its instruments can make measurements that will complement Voyager and EMAP data from a third location in the outer solar system. The EMAP data will produce specific and consequential results on several scientific questions. For the physics of the Heliopause, the first ENA maps will directly constrain the temperature and velocity structure of the heliosheath across the entire sky, not just at the 2 points where Voyager crossed. This will determine whether the 30,000 to 50,000 Kelvin plasma is a local feature of Voyager's crossing locations or a global property of the Heliopause's hot boundary layer. This distinction matters enormously for understanding the physical mechanism. A global hot layer implies a systematic process operating across the entire boundary. A local hot zone might reflect local conditions in the interstellar environment. The heliosphere is currently moving through. For the magnetic alignment finding, ENA maps encode information about the direction of the interstellar magnetic field through the geometry of the ibex ribbon and the anisotropy of ENA emission in different directions. If the ribbon's position in the sky is precisely consistent with the interstellar field being aligned with the heliospheric field, as the Voyager measurements suggest, this would provide strong evidence that the parallel magnetic alignment is a systematic feature of the heliosphere, not a local accident of where Voyager happened to cross. For the IBEX ribbon, IMMAP improved instruments will determine whether the ribbon has internal structure, whether its brightness and width vary along its length in ways that match the predictions of the secondary ENA model, and whether there are features within the ribbon that could distinguish between competing explanations. If the ribbon's structure is fully consistent with the interstellar magnetic field tangency model, this will confirm the direction of the local interstellar magnetic field with unprecedented precision. For cosmic ray shielding, IMMAP, detailed map of the heliosheath's ENA emission, will constrain the thickness and structure of the heliosphere's boundary in different directions, providing the inputs needed to model the directional dependence of cosmic ray attenuation through the heliosphere. This has direct relevance to mission planning for human spaceflight beyond the magnetosphere. For future missions, IMMAP characterization of the heliosphere will inform the science case for an interstellar probe, a proposed future mission that would travel 1.0 from the Sun over approximately 50 years, carrying dedicated heliospheric science instruments into and beyond the heliosphere, complementing IMMAP remote sensing with direct sampling of the boundary and interstellar medium at multiple locations. The science case for interstellar probe depends directly on what IMMAP clarifies and what NEW questions it reveals. Here is what the three Voyager surprises, the IBEX ribbon, and IMMAP mission together reveal at the deepest level. The heliosphere is the Sun's contribution to the environment of its planetary system. It is the physical manifestation of the Sun's influence on the space surrounding it, extending far beyond the planets, creating a distinct volume of space with property S, controlled by the Sun, rather than by the interstellar medium. The heliosphere is what makes our solar system a bounded domain, rather than a region of the interstellar medium that happens to contain some planets. And the heliosphere is not what the models said it was, not completely wrong. The basic structure is correct. Solar wind expands outward, slows at the termination shock, fills the heliosheath, and meets the interstellar medium at the heliopause. This general picture is confirmed by the Voyager data. But the specific properties of the heliopause, the temperature, the magnetic configuration, the permeability, the asymmetry, are each different from what the models predicted in specific and significant ways. The models were built without direct data from the boundary. They were built on indirect measurements, on theory, and on simulations calibrated to conditions observable from within the heliosphere. When direct data arrived, from two probes that took 35 years to reach the boundary, the specific properties measured at two specific points did not match the model predictions. The scale of the discrepancy is worth noting. The temperature at the heliopause was modeled to fall in a range far below the measured 30,000 to 50,000 Kelvin. The magnetic field was predicted to differ in direction inside and outside the boundary. It was measured to align. These are not small corrections. They are significant discrepancies that require physical explanations the models did not include. There is a specific historical parallel worth noting here. In the early 20th century, the interior structure of the Sun was entirely unknown. It could only be studied through its surface emission. The development of stellar physics, the theory of how ion powers stars, how energy moves through stellar interiors, how stars evolve over their lifetimes, was built on physical principles applied to observable surface properties. It was enormously productive, and gave us a robust understanding of stellar evolution. But the specific properties of the solar interior were not directly measured until the development of heliosseismology and, eventually, solar neutrino detectors. And, when those direct measurements arrived, several aspects of the standard model require revision. The heliosphere is in an analogous position. The boundary physics was understood through physical principles applied to observable properties from within the heliosphere. When direct measurements arrived from two spacecraft that crossed the boundary, those measurements showed that specific properties were not what the models predicted. The revision of heliospheric boundary physics that a map will enable is the equivalent of helioseismology for the heliosphere. The first truly direct measurement of the place where the model predictions can be tested against physical reality. A map will determine whether the discrepancies found by Voyager are local, found only at the specific points where Voyager crossed, or global, characteristic of the heliosphere's boundary as a whole. This distinction matters enormously. Local discrepancy S might reflect the specific interstellar environment the Sun happened to be moving through in 2012 and 2018. Global discrepancies would require a fundamental revision of how the heliosphere interacts with the interstellar medium as a whole. And there is something more quietly significant about what a map represents. Voyager 1 was launched in 1977 to study Jupiter and Saturn. Nobody on the team in 1977 expected to still be running the mission in 2012. Nobody expected that the spacecraft would still be receiving science data from interstellar space in 2026. The Heliosphere science that Voyager has produced is science that was never part of the mission plan. It happened because the spacecraft outlived every expectation and kept traveling, kept measuring, and kept surprising the scientists who built and operated it. HEMAP is the first mission specifically built from the beginning to do heliospheric science at scale, with instruments designed for exactly the measurements needed. Launched now, when the questions have been defined by what Voyager found, and what IBEXMAP D. The knowledge gap between what Voyager showed exists and what IBEX measured at limited resolution has been sitting open for more than a decade, waiting for an instrument capable of answering it. That instrument is now operational. What NASA found at the edge of the solar system, using two spacecraft that have been traveling for nearly 50 years, was a boundary hotter, more magnetically complex, and more asymmetric than any model predicted. What IMAP is now finding, using a mission built specifically to answer the questions Voyager raised, will be the first scientifically comprehensive answer to what the edge of our solar system actually is. And the scientists running that mission are paying very careful attention to every measurement it returns. There is one more thread connected to this story. The heliosphere, by shielding the solar system from galactic cosmic rays, affects not just the radiation environment of the inner solar system, but, potentially, the Earth's climate over geological timescales. Some researchers have proposed that when the SU-N passes through dense interstellar clouds, the heliosphere is compressed to a fraction of its current size, allowing cosmic rays to reach the inner solar system at much higher rates. Higher cosmic ray flux at Earth changes the ionization of the atmosphere, which affects cloud formation, which affects climate. The specific geological record of Earth's long-term climate has some features that have been interpreted as potentially consistent with variations in cosmic ray flux on timescales related to the Sun's orbit through the Milky Way. Whether the connection is real, and whether changes in heliosphere size driven by interstellar environment encounters can produce climate effects detectable in the geological record, is one of the most speculative but also one of the most interesting questions at the intersection of heliospheric science and Earth history. Map, comprehensive characterization of the heliosphere's current state, combined with models of how that state would change under different interstellar conditions, is the most direct available path toward testing this hypothesis. That is a story for another time. We started in Pasadena in 2012, when Voyager 1 crossed the Heliopause after 35 years of travel, and the data it sent back did not match what anyone had predicted. A compressed plasma layer at 30 to 50 Kelvin at a boundary that models had described as much cooler. A temperature so anomalously high relative to model predictions that popular coverage named the region the Wall of Fire. Even though the plasma density is so low that the spacecraft passed through it without any thermal effect. Magnetic fields, inside and outside the boundary, aligned in the same direction when the models said they should differ. A result so unexpected that NASA waited for Voyager 2 to reach a completely different portion of the Heliopause, on the opposite side of the solar system, before describing it as confirmed. 6 years later, Voyager 2 confirmed both surprises and added a third. The boundary was thinner on its side, suggesting the heliosphere is not the uniform structure the standard model assumed. Then, we followed the questions those discoveries raised. What physical mechanism produces the extreme temperature at the heliopause, magnetic pressure trapping of energetic particles, or some other process, not in the models? Why are the magnetic fields parallel, inside and outside the boundary, when the models said they should differ? Does the heliosphere reshape the interstellar field in its vicinity? Is it coincidence? Or is there a coupling mechanism not previously identified? What is the ibex ribbon, discovered in 2009 and still incompletely explained in 2026? Brighter than surrounding regions in ENA emission, tracing a great circle around the heliosphere that none of the standard models predicted. And how does the heliosphere's structure, whatever it actually is, determine the cosmic ray environment throughout the solar system? From the astronauts planning to fly to Mars to the cells of every living thing on Earth's surface. And then we arrived at the present moment. September 24, 2025. EMAP launches from Launch Complex 39A at Kennedy Space Center, the same pad that sent humans to the Moon. January 10, 2026. EMAP reaches L1. February 1, 2026. The 2-year primary science mission begins, with 10 instruments covering everything from solar wind ions and electrons to interstellar dust and ultraviolet hydrogen emission, with the 3 ENA imagers, IMAP Low, IMAP High, and IMAP Ultra, beginning to build the first comprehensive global map of the heliosphere's boundary at 30 times IBEX capability. The Voyager surprises define the questions. IMAP is answering them, the results are coming in. The physical mechanism producing the 30 to 50 Kelvin temperature at the heliopause has not been confirmed. Magnetic compression and particle trapping, the most commonly invoked explanation, can qualitatively explain the temperature increase. But quantitative confirmation requires measurements of the plasma conditions across the full extent of the hot boundary layer, not just at the 2 specific points where Voyager crossed. If the hot layer is present everywhere on the heliopause, and not just at the 2 Voyager crossing points, it implies a systematic energy deposition mechanism operating across the entire boundary. If it is present only locally, it implies specific interstellar conditions at Voyager's crossing locations. IMAP ENA maps will train the spatial extent of the hot layer for the first time. The cause of the parallel magnetic field alignment, inside and outside the heliopause, is not fully explained. 3 possibilities. coincidence, heliospheric reshaping of the interstellar field, and a physical coupling mechanism, have not been distinguished by available data. The measurement itself is secure, confirmed by two independent probes at two different locations. The physical interpretation is not. The ibex ribbon's physical mechanism is not confirmed despite 17 years of study. Improved measurements will determine whether the ribbon's detailed structure, its width, its brightness variation along its length, and any fine structure within it, is consistent with the secondary ENA model or requires a different explanation. Both outcomes are scientifically valuable. Confirmation would constrain the local interstellar magnetic field direction with unprecedented precision. A contradiction would require new physics. The significance of the heliosphere's asymmetric boundary, thinner where Voyager 2 crossed than where Voyager 1 crossed, remains unclear. Whether this reflects a systematic asymmetry of the heliosphere related to its direction of motion, or a local variation related to the specific interstellar environment at those locations, requires the global coverage that a map will provide. And the connection between the heliosphere's long-term variation, as the Sun moves through different interstellar environments over its galactic orbit, and the Earth's climate history over geological timescales remains speculative and largely untested. MAP's data will provide the most accurate baseline yet for modeling how the heliosphere would behave under different interstellar conditions, and, potentially, the observational foundation for testing whether the Sun's passage through dense interstellar CLU-DS has left detectable signatures in the geological record. First, spacecraft that outlive their intended missions provide science that no planned mission could have produced. Neither Voyager was designed to study the Heliopause. Both are still providing interstellar science nearly 50 years after launch. The ongoing operation of aging spacecraft, maintained against significant engineering challenges as power systems degrade and instruments fail one by one, represents one of the most scientifically productive investments in NASA history, producing discoveries that defined an entirely new field of observational science that did not exist when the spacecraft were designed. The decision to keep maintaining Voyager through its interstellar journey, even as the science return per dollar declined and the personnel involved in the original mission retired or passed away, is a case study in the long-term return on patient scientific investment. Second, models built on indirect data are revised when direct data arrives. The heliosphere models built over decades of indirect measurement did not predict the Voyager findings. This is not a failure of the modelers. It is the expected outcome when direct data finally arrives from a region previously accessible only by inference. The solar corona presented the same challenge. For decades, theorists modeled it from spectral observations and ground-based instruments, producing models that were approximately correct about the general structure, but missed specific properties that only direct in situ measurements from spacecraft like Parker Solar Probe revealed. The heliosphere is the next domain where this gap between indirect inference and direct measurement is being closed. Third, unexplained features of well-studied systems deserve more attention than they receive. The ibex ribbon has been in the observational record for 17 years and remains incompletely explained. It is visible in every ENA map of the heliosphere ever produced. It is one of the most prominent unexplained features in heliospheric science. Its explanation will reveal something specific and important about the local interstellar magnetic field, which is itself a window into the large-scale magnetic structure OF, the Milky Way in the solar neighborhood. The ribbon is not an obscure detail. It is a major feature of the heliosphere's observable structure that the current models cannot fully account for, and it deserves to be better known. Fourth, the moment between a significant scientific surprise and its resolution is itself scientifically productive. The gap between Voyager's discoveries and IMAP measurements has generated substantial theoretical work aimed at explaining the surprises. Papers proposing physical mechanisms for the hot plasma layer. Papers modeling the interstellar magnetic field alignment. Papers attempting to reproduce the ibex ribbon with secondary ENA production models. All of this work was triggered by the Voyager surprises and refined by ibex observations. Whether or not any individual paper correctly anticipated IMAP results, the body of theoretical work produced represents a genuine advance in physical understanding, because the process of trying to explain specific surprising observations is how physical theory develops. IMAP will now test this body of theory against the most comprehensive measurements of the heliosphere's boundary ever produced. Fifth, what we call the solar system has a boundary, and that boundary is less understood than most people realize. The heliopause is not just a scientific definition of where the sun's influence ends. It is a physical structure, a dynamic, asymmetric, partially permeable frontier between the solar wind and the interstellar medium, whose specific properties determine how well the solar system is protected from the galactic environment. Those properties were not known from direct measurement until 2012. THI are still not fully understood in 2026. IMAP is producing the data that will change that. The edge of the solar system is not a line on a diagram. It is a physical place that we are still, right now, learning how to describe, and where every measurement T reveals that the description needs updating. Voyager 1 and 2 were launched in 1977 to study Jupiter, Saturn, Uranus, and Neptune. 49 years later, they are in interstellar space, providing data that reveals a boundary hotter, more magnetically complex, and more permeable than the models predicted. What does this trajectory, from mission objectives completable in a decade to science that spans half a century, tell us about how to plan spacecraft missions and how to allocate resources for maintaining missions far beyond their original design lifetimes? The heliosphere shields the solar system from galactic cosmic rays, and its effectiveness depends on the structure and thickness of its boundary. If IMAP confirms that the heliosphere is significantly asymmetric, with some directions providing less shielding than others, what would be the appropriate scientific and practical response? Does this change how we plan human spaceflight routes? Does it affect how we model the radiation history of the inner solar system? And the most fundamental question. We have been aware that the solar system has an outer boundary since the heliosphere concept was developed in the 1950s and 1960s. We have had spacecraft at that boundary only since 2012. What does this specific, datable moment, when direct data from the edge of the solar system first became available, reveal about the limits of what indirect observation can tell us? And how much of our understanding of familiar objects like the solar system may still need to be revised as direct exploration continues? If this one stayed with you, let us know which part landed hardest. The Voyager 1 crossing in 2012, and the three things the data showed that didn't match any model. A plasma layer at 30 to 50 Kelvin. Magnetic fields aligned when every model said THI should differ, and a boundary thinner on one side of the solar system than the other. The ibex ribbon, discovered in 2009, still without a fully confirmed explanation in 2026. Or the current moment. IMAP science mission began February 1, 2026, with 10 instruments at L1. Building, the first global measurements of the heliosphere's boundary at the resolution needed to answer the questions Voyager raised, and the results are coming in right now. And if you want more of this, real space science at the frontier of what we know, subscribe to Galaxy Pulse, and we will see you in the next one. In 1977, 2 spacecraft launched toward Jupiter. In 2012, one of them crossed the edge of the solar system. The edge was not what anyone expected: hotter, magnetically unexpected, asymmetric, permeable. In 2026, a spacecraft, built specifically to answer the questions Voyager raised, is measuring the heliosphere's boundary for the first time at the resolution needed to understand it. The data is coming in now. Whatever it shows will be the most complete picture of the boundary of our solar system that has ever existed. And, whatever it shows, the boundary itself is already less understood than we thought. 50 years of travel, and the edge of the solar system is still surprising us. The Voyager program at 50. A note on scientific time: there is a dimension of the Voyager story that deserves explicit attention, because it speaks to something important about how science operates on the timescales of actual discovery. When Voyager 1 and 2 were designed in the early 1970s, the goal was the Grand Tour, a once-in-175 years alignment of the outer planets that would allow a single spacecraft trajectory to visit Jupiter, Saturn, Uranus, and Neptune by using each planet's gravity to redirect the spacecraft to the next. This opportunity opened in 1977 and would close within a decade. The spacecraft were designed to accomplish this planetary tour, with a design lifetime of 5 years. Nobody designed Voyager to study the interstellar medium. The instruments that ended up providing the most significant heliospheric science, the plasma wave instrument, the magnetometer, the low-energy charged particle detector, were included for the planetary mission. As the spacecraft completed their planetary encounters and continued outward, the instruments that were still working decades later became the sensors that would detect the termination shock, traverse the heliosheath, and eventually cross the heliopause. The heliospheric science that Voyager produced was emergent science. Science that emerged from the longevity of the mission and the survival of specific instruments. Science that no mission planner in 1977 could have specifically designed for, because the specific scientific questions that would drive this work had not yet been formulated. This is not a unique feature of Voyager. It is a recurring feature of long-lived space science missions. Cassini's discoveries at Saturn, in its final orbits, diving between the planet and its rings, were discoveries that the mission designers in the 1990s had no specific plan to make. Hubble's observations of the large-scale structure of the universe, measuring the rate at which cosmic expansion is accelerating, were not part of the original Hubble science case. They became possible because the telescope was working, pointed at the sky, and used by scientists whose questions evolved with what they found. IMAP is the planned mission that Voyager's accidental discovery made necessary. But the next IMAP, the mission that will answer the questions IMAP reveals, does not yet exist, and the science it will address has not yet been fully formulated. Because the results that will define those questions are still coming in from instruments that began their science mission 5 months ago. What the edge of the solar system will continue to reveal, through the instruments that survive long enough to ask the right questions at the right moment, is a story that will be told over decades. We are at one datable chapter in that story, the IMAP chapter, where the questions Voyager raised are being specifically answered for the first time. The chapter after this one is still being written by the discoveries that IMAP itself will produce.